this is part 2 of the series lecture. We're going to do an example problem real quick. No big deal, just a couple slides here. And in this example, we have a 120 volt supply. Now, voltage drop is something you can measure with your meter, right? You can always measure voltage drop. So let's look at E1. We can measure across this resistor and see that we have a 10 volt drop. Across E2, we have 25 volts. Across E3, we have 50 volts. At E4, we have no information except the resistance, that the resistor of E4 is 10,000 ohms. So let's look at our next slide. 10K ohms. 10,000 ohms. Okay. So we know that E total is equal to E1 plus E2 plus E3 plus E4. So if we just subtract everything that we do have on the right and subtract it from the left, we get ET minus all the voltage we can see. We only have one left over that we don't have, right? So if we have ET minus E1 plus E2 plus E3, that'll give us E4. Is that correct? So if we subtract, or we can just add 10, 25, and 50 together and subtract it from 120, right? So that would be 75, 85 from 120, which is 35 volts left over, right? So we know that the voltage drop across resistor 4 must be how many volts? 35 volts. Okay, now if that's true, we have a voltage and we have a resistance, right? So if we have a voltage and we have a resistance, we can do what? We have a voltage and we have a resistance. If we divide those two, that will give us the current. All right. So if we divide, what was it, 35 volts by 10,000 ohms, that's pretty simple. If we're divided by 10,000, we just move the decimal place, what? 10, so 10,000 is 1 and 1, 2, 3, 4, 0. So we're going to move the decimal place 4 places to the right, right? So it's 0.0035, right? Well, get your calculator out, divide 35 volts by 10,000, and it should say 0.0035. So now we know that we have a current at I4 of 0.0035. How many would we say 0.0035 on a quiz answer sheet? No, we would not. We would say what? 0.003. 3 is milli, right? So we'd say 3.5 milliamps. Sorry. We're talking about current here. Okay, so we're talking about 3.5 milliamps. So if we have 3.5 milliamps everywhere else, we can plug that in everywhere around the circuit. So now we can just run around and plug in. We had 35 volts here that we found, and we 0.0035 and 0.0035. And also, I already plugged it into the current total, so that's our current total also, right? Okay, so now we have two things in E1. We have two things in E2. We have two things. We already had two things in E3, E4, and then we have two things in E3. So we can just run around and solve each branch, as we say. And let's do that. If we have 10 volts and we divide by 0.0035, aren't we just moving the decimal point again? So, let's see. Oh, we went and found the totals. We could go over and find the total. We want to divide 120 by, let's see, 0.0035. And that'll give us 34,285.7 ohms, right? We wouldn't write that as a total either, would we? We'd write 34.285 or somewhere around there. K ohms. So 34,285.7 ohms. Okay. And let's do our other resistors. And let's find, if we just multiply up, we could get our power on E1 really easily, or total power. If we just multiply I times E gives us power, right? We're not going to do that today. We're going to work on that another day. But if we divide 25 by 0.0035, what will we get for resistor 2? Pull out those handy dandy TI-30X2S's. Okay, so if we divide 25 by, one more time. If we divide 25 by 0.0035 amps, we get 7,142.8 ohms. And then if we divide 50 volts by 0.0035, how many ohms will we get? 14,285.7 ohms. Okay.
0.714 if you want it.
Say again?
0.714 if you want to go to hundreds million.
So now, oh, I didn't do the one where we divided 10 by 0.0035. Let's do that. We need a total there.
2,857.4.
2,000. Point 1. All right. Now, let's add as a cross. Now, we could do a cross check here. And we could add our resistance 1, resistance 2, resistance 3, and resistance 4 up. And we should come close to 34,285.7. So let's add up 2,857.1 plus 7,142.8 plus 10,000 plus 14,285.7. And what would we get? All right, so when we add these up, because we rounded a little bit, we wound up with a total of 34,285.6. And as I've said many times, that's close enough for the girls I go with. It's only 1/10 off. I think I can live with that. Actually, a little less than that, but that's okay. Okay, so have we figured out everything in this circuit? Somebody say yes.
Yes.
Okay. All right, so this is example number 3. We're going to assume we have 48 volts supplying a circuit with a lot of resistance. So that means the current flow is going to be really small, right? Okay, so what we know is we have a 48 volt supply. And we have 250 ohms in resistor 1, 502, and 2,500 ohms in resistor 4. And resistor 3, we don't know anything about it. But look at this. We have a resistance total. And we have a voltage supply. We could get the current, couldn't we? That's almost too easy, isn't it? Okay, well, let's do that. Let's take a calculator and divide 48 by 4,500. You already did that? Excellent. 0.01066. Okay, that's a good number. And that is what? Amps. Would we say 0.0106 amps? We would not. We would say 10.6 milliamps, right? 10.6 milliamps. If nothing else, this is a good review of engineering notation. Now let's go up. Now we've been talking about we could do this in the past. Let's do that now. Let's multiply. Now we have 0.0106. Let's multiply that times 48, and we'll get our power total, because P is equal to I times E, right? So let's multiply I times E, 0.0106 times 48 gives us, say again?
51.2 milliamps.
Much better. 51, no? Is it 0.51 or 0.05?
0.512
Okay, that's 512
milliamps.
milliamps. 512 milliamps. So that's a good example. I'm glad we did that because making a mistake sometimes helps more than getting it right. So let's go to the next one, and what can we plug in? Oh, we should find R2. I like that better. Let's find R2. Now, what's the rule we need to apply here? RT is equal to R1 plus R2 plus R3 plus R4. But that really doesn't help us much, does it?
Current is consistent.
We're going to find the resistance for R3. Now, what we really want to know is if we have everything except R3, right? So if we subtract R1, R2, and R4 from RT, we'll get what? So RT minus quantity R1 plus R2 plus, which one do we not know? R3. R4 is equal to R3, right? Okay, let's put some numbers in that. We have a total, don't we? Okay, 4,500 minus 250 plus 500 plus 2,500. Now to simplify, we could just add that together. 250 plus 500 plus 250 would be 3,250. Is that correct? Okay, let's take this out. What was that? 3,250. And that's going to equal what?
R3.
R3 is what? We think it's 1,250, right? All right. Oops. That's right. Okay. So now we have two things in every box because we're going to go around and add our current. Put that in blue. And so now we're just going to multiply up in the case of R4, 2,500 times 0.0106. Okay, so if we multiply up 2,500 times 0.0106 amps, we get 26.5 volts. If we multiply 1,250 ohms times 0.0106 amps, that's what's all jumbled right there. That's okay. Let me write that a little clearly. Oh, it wasn't that special. Okay, and that was, wow, stop. All right, so if we multiply 1,250 times 0.0106, what do we get? Thank you. 13 point what? 25 volts. Very good. And we can multiply the same number by 500. Okay, so we multiply 500 times 0.0106 times 500, we get 5.3 volts. And our last one, if we multiply it times 250, we got 2.5 plus 1.5. 6, 2.65 volts. I think that's correct. All righty. Now, I think we've solved for everything except the power in each resistor, but that's okay. I can live with that. You guys can see that you can do that. Now we're going to go on. Oh, I just went past 15 minutes. Damn it. All right, we're going to stop here.